All right, welcome everybody. The recording is in progress. Walt, I'll hand up right to you to be the chair of our today's session.
Okay, thanks, Dirk. So welcome everybody to this Laws of Nature seminar. And today it's a pleasure to have here with us Jeffrey Barrett and Eddy Chen. And so Eddy Chen is going to present their recent work on algorithmic randomness and probabilistic laws. So Eddy is from the University of California, San Diego, and Jeff from Irvine. And so the talk will be about an hour, and then there's time for questions. So if you have any questions that are necessary for following the talk, please ask them. If they're more substantial, please wait until the end. Okay, Eddy, please go ahead.
Thank you so much, Ward, and thank you, Dirk, and organizers for the kind introduction and for inviting me to be here. It's great to see everyone here, and I see Barry and Jennifer and many others. Thank you for being here. So I would like to discuss a radical idea about probability, randomness, and laws. This has many surprising features, but if it is correct, we have found a new solution to some of the difficult problems in the foundations of probability and philosophy science, with ramifications for both humanism and non-humanism. So this work is in joint work with Jeff Barrett, and we're working on extending this project to other theories. So my plan is to give a talk, answer some easy questions, and leave the hard ones to Jeff. Okay, all right, let me start. The concept of probability has many aspects. It's related to our beliefs and credences, what's in our minds, and related to the world, what's out there. Our focus is on probabilistic laws of nature. Those laws that involve probabilities in their various statements, such as probabilistic laws in quantum mechanics, think about collapse postulate, and statistical mechanics. We develop a new conception probability, we call it probability star, and develop a new approach to probabilistic laws. We call it probabilistic laws star. The key is to use algorithmic randomness. And this has relation to conceptual issues about probability, such as scientific explanation, randomness, independence, typicality, objective probability or chance, the principle, and perhaps Cornell's principle. So some background. So Jeff came to this interest from interest in foundational quantum mechanics, and I came to this topic from works in laws of nature and thinking about typicality and Cornell's principle, what is very likely, what will happen. So there's a convergence of interests here and convergence of topics. That's why I think it's very exciting to share this research with you all, because it has many, I think, implications. Okay. Probabilistic laws, as they're usually understood, involve a variety of other determination. Here's a simple example. Consider repeated tosses of a coin. It produces an infinite omega sequence of results or outcomes. Say heads, heads, tails, heads, tails, heads, heads. Say 1, 1, 0, 1, 0. So we call this as R1, R2, R3, ... as an infinite sequence. Goes on forever. The actual outcomes. Right? Now, each possible sequence of the possible outcomes describes which we call a possible world. It's a simple possible world, just coin toss outcome, nothing else. Now, let omega L be the set of all such worlds that accord with the law L, or compatible with law L. Consider the following probabilistic law L. Each element in the omega sequence of coin tosses, R1, R2, R3, ... is determined independently and with unbiased probability of heads and tails. So one might think of L as descriptive fundamental random process, something like starting with a sequence of spinning half particles, say particle 1, particle 2, particle 3, and to particle infinite, and each in eigenstate z spin, then measuring their x spins in turn. And the outcomes will be heads, heads, tails, or up, up, down, so on. So it'll be 1, 1, 0, 1, 1, 0. Okay. So this will give you a possible sequence. Now, the probabilistic law L says its unbiased probability, so 50-50, has tails independent. So no influence from the first toss to the second one, or second one to the third one. So independent determination. That's the law L. And it's kind of schematic for typical standard probabilistic law we find in physical theories, we find in mathematical theories. Now, as probabilistic laws are typically understood, omega L is the set of all omega sequences. That is the sequence of all, it's the set of all 0-1 sequences. L does not rule out any world. It is very permissive. A world compatible with L might exhibit any limiting record frequency or no limiting record frequency at all. For example, it's compatible with the all-one sequence, the all-heads world. It's compatible with a world with 1/3 heads, 2/3 tails, even though L says unbiased frequency and independent. Even the full history of a world will fail to determine L, not in one case or two cases, but in a continuous cardinality of cases, infinite many cases. Now, even the full set omega L does nothing to determine L over any other probabilistic law. Suppose L prime says, it's not unbiased frequency, but 1/3 heads and 2/3 tails. It is still compatible with the full set omega L. Any sequence compatible with first L is compatible with second L prime. This undetermination is closely related to empirical coherence. So we should define this in this paper as follows. A physical law is empirically coherent only if it is always, in principle, possible for one to have empirical support for the law if the law is in fact true. And this is related to earlier works by Jeff Barrett on empirical coherence in quantum mechanics and records. Now, if a law is empirically incoherent in the sense defined, then it may be impossible to learn that the law is true even with complete evidence. If you know all the outcomes, actual outcomes, you might still not know the full law. There are omega sequences that might occur, but will provide no empirical evidence whatsoever for accepting L. For example, the all-heads world, right? In such worlds, one will never have any empirical support for accepting the correct probabilistic law, even with full evidence. If you occupy the all-heads world, you will not be inclined to take this to be as evidence for the even distribution law. And there is a continuous cardinality of such worlds. It's not just one or two or three, but infinitely many. We suggest we can get a tighter fit between probabilistic laws and empirical evidence. How? By appealing to a stronger conception of probability and a correspondingly stronger variety of probabilistic laws. Consider law L star. The omega sequence of coin tosses, R1, R2, R3, is or must be random with unbiased relative frequencies of heads and tails. Now, here being random is not, say, some hidden mechanism shuffling things, but we take this to be the property of the omega sequence, first and foremost. It's compatible with there being some mechanism shuffling things, but we just want this to be a property of the actual outcomes. So suppose I give you a sequence of outcomes, you can tell me yes or no, it is random or not. This is called outcome randomness. This notion should be defined, and we'll clarify later. The notions of randomness we're interested here are algorithmic, related to algorithm. Defined in terms of statistical tests to determine whether an omega sequence exhibits any specifiable pattern. Each sequence will either pass or fail a particular test for being random. Okay, remember L, standard probabilistic law L, with unbiased distribution, heads, tails, and independence. L is compatible with all omega sequences of results, and all the 0-1 sequences. Now L star is not. L star is more restrictive. Let omega L star be the set of all worlds that accord with the law L star. All the possible worlds compatible with L star. You can think of this as the physically possible worlds or nomologically possible worlds of L star. All the worlds in L star exhibit the random unbiased sequences stipulated by L star. So it's a proper subclass of omega L. The complement of omega L star in omega L is called ML, the maverick worlds. So omega L star contains no maverick worlds. The weird ones, the bad ones, the strange ones, the undesirable ones. Maverick worlds are those that exhibit a specifiable pattern, will fail to exhibit the right relative frequencies, will fail to exhibit any relative frequencies at all. So that includes the all heads world, the 1/3, 2/3 worlds, the worlds with no relative frequency at all. Now, so we're interested in defining what L star is and think about the space of nomological possibilities, omega L star. If L star is true, then any physically possible world fully determines L star. An L star law is empirically coherent in the relevant sense defined here, while L law is not. That's one major difference. Here's a nice implication. No special probabilistic background assumptions or priors regarding what world one inhabits are required for successful inquiry. Now, the principle, the set your credences to chance, objective chance, and Cornell's principle, right, was overwhelmingly likely will happen, are sometimes used for this purpose, which we'll come back to later. But for L star law, an inquiry in any physically possible world, not most, not the majority, not overwhelming probability, but any physically possible compatible with L star, by determining the truth of L star by considering the results of coin tosses. With complete evidence, one will surely, that is, in every physically possible world, compatible with the law, learning up to an equivalence class of computationally indistinguishable laws. We might still have pragmatic computational limitations, and that might still give rise to some undetermination. But they're a new kind. It is not the same kind as before. Okay. A probabilistic law like L star is much like deterministic law in this way, and which we'll explain. Okay, so here's a plan for this talk. We define the randomness constraint that every L star world must satisfy. We consider two understandings or two metaphysical characterizations of L star law. And 3, we discuss the costs and benefits. And 4, we argue the second understanding has salient virtues. And by the way, feel free to interrupt me for clarification questions. We can save the substantive question to the end. Okay, so let's first define the randomness constraint using algorithmic randomness. We need a test for randomness for omega sequences. Give me omega sequence, I tell you whether it is random or not. A random sequence of tosses with unbiased coin should exhibit even relative frequency of heads and tails in the limit. So I count, okay, how many heads had there been, the second one, the third one, the fourth one, the fifth one, to infinity, right? I see the limit. But this is not sufficient. Here's an example of a non-random sequence, an alternating sequence of heads, tails, 1, 0, 1, 0, 1, 0, 1, 0, to forever. This one has perfect 50-50 distribution, but not random. There are further conditions, 3 further conditions for the unbiased random sequence. First, patternless. Second, generic or typical. Third, doesn't allow for a successful fair betting strategy. You cannot gamble and win unbounded wealth. And here's some references. Now let's start with the first condition. An omega sequence is random only if it exhibits no finally specifiable regularity. So algorithmic tests are helpful characterizing what is patternless without pattern. First pass, say an omega sequence is patternless and hence random, if and only if there's no finite length algorithm that produces a sequence. It might be right for the 101010 sequence, because for that one, there's obvious algorithm, which is repeat 10 forever. Very short, maybe a few characters. But this is, okay, so a finite length algorithm would express a regularity, something like a deterministic law, a simple law. So in that case, you might think it's better than the probabilistic law. Now, but the first pass criterion is insufficient. For example, consider a 3-block pattern. We have one block that's all heads, 1, 1, 1, 1, 1, 1, 1,000 heads, and one block that's all tails, 0, 0, 0, 0, all 0, 1,000, and a random looking block, 1, 0, 1, 1, 0. So random looking block with the right distribution 50-50, but it's random looking, and it's also 1,000. And repeat this, right? Again, again, and again. So 1 block, 0 block, and random block. And 1 block, 0 block, random block. In this sequence, this infinite sequence, the relative frequency of heads and tails in the full sequence is unbiased. And the sequence cannot be represented by a finite length algorithm. You can capture this and this, but to capture the whole sequence, since there are infinite many random blocks, it requires infinite long algorithm. Right. So the sequence passed the first pass criterion, but isn't random. The sequence is not random. And for example, can design a gambling strategy and enjoy unbounded wealth by just betting on 1s and 0 in the first 2,000, and then don't bet anything at all for the third. So the problem is there is no amount that the final initial segment of sequence can be compressed. You can always compress more and more and more. For every 3,000 tosses, you can compress by 2,000 at least. One might write a very short program that takes advantage of the regularity. And one can eventually shorten the algorithm representation by more than any constant c. So for any number c, you can always make the sequence shorter by c, more than c. And this observation provides a key idea behind Kolmogorov-Chaitin randomness definition. A non-omega sequence is Kolmogorov-Chaitin random if and only if there's a constant c such that all the finite initial segments are c incompressible by a prefix-free Turing machine. So in the previous case, it is not Kolmogorov-Chaitin random, the 3-block pattern, the 3-block sequence, because there is no constant c such that all finite inner segments are c incompressible. You can always go shorter than, and you can always go more than any finite number c, so that the whole sequence can be compressed. Okay, it's the first definition of randomness, called patternless randomness. And that's Kolmogorov-Chaitin. Let's turn to the second condition regarding generic or typical. And this is something that should be familiar to those who are thinking about typicality and statistical mechanics, because similar questions arise here. So the first pass criterion is that an omega sequence X is random only if X satisfies all typicality properties. But that is too strong. Being different from X, whatever X is a typicality property. Is had by almost all members of the set, right, in the infinite case. And this will imply that no omega sequence is random, but because no omega sequence will have the property being different from itself. So we need to restrict the class of typicality properties in a principal way. Martin-Löf offers a remarkably simple and satisfactory solution. And this is the foundation for Martin-Löf randomness. An omega sequence is Martin-Löf random if and only if it belongs to every effective full measure set. That is, it belongs to no effective measure 0 set. So what is an effective measure 0 set? So this is basically a characterization of an effective atypicality, right? So suppose we have the full set, the 2D to omega, the counter space, the set of all 0, 1 sequences of infinite length, then a set E in 2D to omega is effective measure 0, just in case there is a uniformly effective sequence open sets G1, G2. So let me write this in this form. Suppose I have a sequence of sets G1, G2, and G3. All of them includes E as a subset, and such that the sequence gets increasingly small. And this sequence of sets can be determined by a single algorithm. In this case, E is effective measure 0. Now, an omega sequence is not Monte law of random, just in case it belongs to one of this effective measure 0 set. That is, can be characterized by some kind of single algorithm such that it is in some set, including all of this sequence. Now, this is characterized by Monte law of random. If we apply this to the previous case, you will see that this also rules out the 3-block pattern as non-random. How so? So in this case, we have a 3-block pattern. Right. Now, this, you can design an algorithm, and that gives you a sequence of open sets, such as, suppose you have open set G1, that is all the omega sequences are beginning with 1,000 ones, 1,000 ones, 1,000 zeros, and says nothing about the random block. And this includes many sequences of this form, including this one, right? This being particular case. And G2 says, okay, this is a setting which all the sequences with 1,000 ones, 1,000 zeros, says nothing about this, and also 1,000 ones, 1,000 zeros. Okay, and G3 similarly says all of this plus 1,000 1,000 zeros. Okay, so this you construct a sequence of open sets that includes this one and gets increasingly small. And therefore, this is a member of one of the effective measure 0 sets, and therefore it is not random. Now, this illustrates a general phenomenon, which is that Monte law of randomness and Kolmogorov randomness are equivalent, even though there seem to be different definitions. One are patternless, is there a pattern in the sequence? One are typicality, is it typical or is it exceptional? So an omega sequence is Monte law of random, if only if it is Kolmogorov charting random. And moreover, there's a way to think about the Betting criterion in terms of martingale, such that it is equivalent as well to the two definitions. So the upshot is that Monte law of randomness is simple and natural, and very surprisingly, it is equivalent to similar different characterizations of algorithmic randomness. So 3 definitions of randomness: patternless, typical, and doesn't allow for betting strategy, they converge in the same notion. They're equivalent. So just as you have the Church-Turing thesis in computation, you might have Monte law of charting thesis for randomness. That is, seemingly different characterizations make rigorous enough converge to the true definition of randomness, the Monte law of randomness. Okay, this one thesis you might adopt. Okay, we don't need something so strong for the paper, but just want to mention this for motivation for considering this definition. Now, we've used Monte law of randomness to specify law L star. So we're going to use this as the characterization for L star law. As a constraint on a set of physically possible worlds, call this law L star ML. The omega sequence quantizes R1, R2 is Monte law of random with unbiased relative frequencies, pairs, and tails. And because of equivalence, it's also Kolmogorov charting random, and random in the definition of Betting criterion. Here, all the worlds in omega L star ML are random with well-defined unbiased relative frequencies, and randomness specified by Martin-Löf. Hence, in this situation with L star law, a non-dogmatic inquiry will surely learn if for unbiased relative frequencies in the limit. Inasmuch as all initial segments for data will be C-incompressible, she will have as good of evidence as possible that data are patternless and hence random distributed. Just by this, we know in that there's epistemic implications of this law, not just kind of a metaphysical or mathematical definition, but there's implication for learning theory. So there's work by Francesca Brando and others on this connection between algorithm randomness and Bayesian convergence to the truth and so on. So there's really fruitful connection to issues about learning theory, how we should update. Okay, now just for completeness, I'm just mentioning quickly that Martin-Löf randomness is not the only way that one might characterize the probabilistic coin toss law. There are other notions to choose from, such as Schnorr randomness, another popular notion, closely related with many same virtues. It is different though. So Schnorr test is a special kind of Martin-Löf test requiring not just effect measure 0, but also that the measures themselves can be uniformly computable. So the numbers themselves can be uniformly computable. And in this way, this is going to be a much, it's a less restrictive kind of law. So we can specify a law in terms of Schnorr randomness. And the Schnorr randomness sequences will be a proper subclass of omega L, but a superclass of omega L star ML. So it's between omega L and omega L star ML. Okay, there are some sequences that are Schnorr random but not Martin-Löf random. So the two are different laws. So different laws, but they're in a strong sense empirically equivalent. So in some sense, it doesn't matter which one we choose, even though they are distinct, right? There's no effective procedure that can determine whether a particular sequence is Martin-Löf random or Schnorr random, but not Martin-Löf random. This is proven by a paper by Jeff Barrett and Zaman Heidegger in Philosophy of Science. Now, if one limited to Turing strength computation, right? There's a benchmark level of computation. One will never be able to distinguish between ML and Schnorr randomness laws, no matter what empirical evidence one had. So moving from a standard probabilistic law to L star law eliminates one variety of determination, but it reveals two others. One should already expect that law L star to be empirically indistinguishable from L insofar as one expects a sequence of coin tosses governed by traditional probability law L to be such that one can detect no determinate pattern. And two, one will be unable to distinguish between different versions of L star like ML and Schnorr insofar as one is limited to Turing strength computations. Now, since Martin-Löf randomness is a standard kind of notion and has sort of properties we want, we're going to stick with Martin-Löf randomness and choose ML instead of Schnorr as a notion for randomness we want. So we understand L star as L star ML in this paper. But it is a choice. It's a choice we have to make. Okay, so if we define what it means to be an L star law in terms of Martin-Löf randomness, it provides a header fit between the law and its corresponding set of possible worlds. So L star and omega L star is very tight. It's quite different from an L law in this sense. Now, let's come to the nature of laws and ask a more philosophical question. What kind of physical law is L star? How does it govern the world? One might think of L star in one of the two ways. First, it's a generative law, productive law, that making things happen sequentially in time. We call this generative Chen star law. And second, it's a holistic constraining law. We call this probabilistic star constraining law. And these are meant to be non-Humean laws. They're not supervening on the mosaic or what actually happens, but really robustly govern and explains phenomena. But these laws can be adapted to Humean interpretations, so they will discuss some implications for Humeanism as well. It's a generative Chen star law. So think of this as a Chen star process, right? So L star tells us that each toss is generated by an unbiased Chen star, where a chance star process behaves just like an ordinary chance process. Say chance process, you have, say, the first one, you have heads and tails with 50-50 probability, and then heads and tails, 50-50 probability, and so on. So sequential generation process. So a chance star process like this, but it can never produce an infinite sequence that fails to be multi-level random or fails to exhibit well-defined relative frequencies. And this means that you can never have a generation with 1, 0, 1, 0, 1, 0 that goes all the way to 1 or all the way to 0 or 1, 0, 1, 0, 1, 0 forever. Not allowed by the chance star process, even though it's allowed by the chance process, right? It's very unlikely, but it can still happen on a chance process. On a chance star process, it is impossible. As a result, a chance star process involves a subtle violation of independence. The sequence of tosses will pass every finitely specifiable test for statistical independence. But since the full sequence must satisfy the constraint imposed by the law, a chance star process is holistically constrained. The constraint is not felt on any finite set of tosses because any finite segments can be allowed by the chance star process, nor is it discovered by any effective means. But it does require that in the infinite limit, the relationship holds between the full sequence of tosses generated by the process in the limit. The interdependence between outcomes may be incompatible with the usual intuitions behind one-hit generative law. Okay. It may also be compatible with how causal explanation works more generally. This is a subtle violation of temporal locality, right? But there's a second interpretation of law L star. Not in terms of production or generation or chance star process, but in terms of a constraint, a holistic constraint. L star can be regarded as a law that governs by constraining the entire history of the world. In this case, the full omega sequence of outcomes. L star tells us which sequences of outcomes are physically possible. So suppose I have the full set of 0, 1 sequences. L star tells us which subset is the physically possible histories and which ones are the physically impossible histories. It draws a line between physical possibility and impossibility at a global level. So the physical possible ones are those satisfying the frequency constraint, say 50-50 distribution, and multi-level randomness imposed by the law. So every one of these must be one that satisfies the frequency constraint and randomness constraint. And I like it in part because it matches well with Chen and Goldstein's view of laws of nature, minimal primitivism about laws, or MIMP, that says laws are certain primitive facts, fundamental facts that govern the world by constraining the physical possibilities of the entire spacetime and its contents. The non-human view in which laws govern, but it's not a view like Tim Mautling's that laws produce things sequentially in time, but it's really kind of holistic constraint, right? So in Ken Wharton and Emily Adams' words, it's like all at once kind of laws, constraining the entire history of the universe. Understood this way, L star addresses problems encountered by both non-human and human accounts of laws. We start with the former and go into the later. So on non-human governing conception of laws, there's a puzzle. Precisely, how do probabilistic laws govern a law like L? From the standard view, probabilistic laws do not rule out any world. Instead, they merely assign some numbers between 0 and 1 to measurable subsets in the space of all omega sequences. This raises the puzzle. What does number between 0 and 1 represent in physical reality? It's not like mass between 1 kilogram and 2 kilograms. It's not like charge. It's not like spin, but some number. Not quite physical. It's not something we can directly measure. But this also objective. It's not purely subjective, right? Between 0 and 1. So some non-Humeans appeal to gradable notions to understand or give a metaphysical interpretation of numbers between 0 and 1. Propensities or probabilities of necessitation. So here's one way to think about this. Suppose we have a probability law like that assigns a 0.2 probability to the next outcome being heads. In the propensity view, we might say the Chen setup, say this coin toss mechanism, has a 0.2 propensity to bring about a heads outcome in the next toss. But what is this notion of propensity again? Okay. And for Armstrong, he would say the current state of affairs necessitates the state of affairs of heads outcome. Not exactly, not completely, but to a 0.2 probability. Okay. So we might think that physical possibility, impossibility, necessity, or necessitation may be clear notions, but things like propensities and necessitation with probability are much less clear. It's like nudges to this possibility to some degree, and away from that possibility to some other degree. But this nudging notion seems very fuzzy and very unclear. In contrast, probabilistic laws such as L star can be viewed as a special class of constraining laws. We don't need this gradation between possibility and impossibility. This complete on-off possibility is all we need. L star laws constrain what's physically possible by ruling out certain sequences of outcomes. Which worlds are ruled out? This field satisfies the constraints. We can do away with gradable notions of propensities and necessitation probabilities altogether. In their place, we only require non-gradable notions like physical possibilities and impossibilities. So consider MIN-P as a non-Humean example. On MIN-P with L star laws, we can now employ a single primitive notion relation, namely constraining. For any type of laws, probabilistic, non-probabilistic type of laws, they all just governed by a single type of relation, by constraining what's physically possible. It's not like constraining for non-probabilistic laws like F equals MA and some other notions for probabilistic laws. The way that L star constrains the world is not so different from the way that F equals MA constrains the world. L star constrains the physical possibility to be all and only those non-Maverick worlds. F equals MA constrains the physical possibility to be all and only in those solutions to F equals MA, picking out physical possibilities. And that's it, just one single notion. So in this way, L star removes a major obstacle to unify understanding of probabilistic and non-probabilistic laws. And this is one of the conditions, one of the options Sheldon Goldstein and I consider in our paper. But I really saw how to work this out with Jeff in this paper because algorithm randomness is such a cool notion. It has all the features we want for probabilistic laws and can use constraint to cash out this notion of L star. Okay, so I think this is a very natural way to understanding governing laws, especially MIN-P, but I think maybe Sheldon Goldstein would disagree with me on this. Let's turn to Humeanism. Even though I'm not a Humean, I like to think of myself as a friend of Humeans and want to help them develop their views in different ways. Let's try L star for Humeans. It turns out it's a great gift to Humeans. Humeans might find it useful to adopt L star for two reasons. For two reasons to do with how to understand probability and connection to the best system account and to the mosaic. First, it's relevant to the issue of the big bad bug. It's a pretty bad problem for humanism if it leads to inconsistency. And Lewis realized on a straightforward kind of analysis of humanism, it does when we connect human supervenience with what's called the principle. So human supervenience means that the law supervenes on the mosaic. The laws given rise to by the mosaic, what actually happens. So the actual outcomes get summarized by some simple statements, and those are the laws. The laws don't produce the outcomes. Laws don't constrain or explain the outcomes. Laws are just merely floating from the outcomes. They're summaries of the outcomes. Now, if you have probabilities in the laws, there might be additional summaries that simplify and inform us about the actual outcomes, but they're not producing things either. So they're on the same status of laws. Okay, now there is the principle called a principle that's also very popular among humans. It says roughly that set your credence, what you believe to be likely or not, to the actual chance. So if some chance process says the chance is 0.2, you set your credence to 0.2 degree. And the two are inconsistent with plausible assumptions. So Lewis realized that certain histories of the human mosaic, called undermining histories, are assigned, according to the principle, non-zero probability, conditionalized on some probabilistic theory T being the best system. Think about the, say, has-tail sequence, given the best system with law L. For the finite round, it has non-zero probability. For the infinite case, it has non-zero infinitesimal probability. But if that world were actual, if that is the actual mosaic, then you never think the best system is the L law. It will be a different law, namely repeat 0, 1 forever. That would be the better system than L law, be more informative. So they are assigned according to human supervenience, zero probability, because T will not be the best system at any of these undermining histories being actual. So is it 0 or not 0? Inconsistent. Now, what sort of history counts as undermining? Those with the wrong radio frequencies, say the 1/3 world, those with no limiting frequencies, or those that containing patterns can be summarized by a simpler system, say the 1010 sequence. Undermining histories, then, are exactly the histories of maverick worlds, as they lack the frequency or randomness patterns exemplified by the typical sequences of standard probabilistic law. Now, star laws rule out maverick worlds. If maverick worlds are physically impossible, then there are no physically possible undermining histories that can lead to contradiction. The Big Bang bug is eliminated. You don't have to give additional stories because this is all you need to get rid of the Big Bang bug. Eliminate them from the space of physical possibilities on principle grounds. Now, in as much as reaching to star laws is motivated also by considerations of underdetermination and empirical coherence, a human might find this solution particularly natural and independently motivated. Second, adopting star laws can also avoid appealing to fit as a criterion in the best analysis of probabilistic laws, which allows humans to bypass difficulties with how to characterize this notion. Given the omega sequence, there's much underdetermination among standard probabilistic laws like L. One is something like fit to choose a winning best system. Strength or informativeness as a quantity of worlds being excluded does nothing to distinguish between among probabilistic laws like L, because L with even distribution and L with one-third distribution are compatible with the same set of worlds, namely omega L. Okay, different candidates compatible with the same set of worlds. In contrast, for L star, there's much less underdetermination among probabilistic laws. Consider different probabilistic laws like L star that differ, say, in the specifications of relative frequencies in the omega sequence. The omega with 1/2 probability, with 1/3 probability. Notice they will be disjoint sets of worlds with no intersection, empty intersection. At most, one of them is compatible with a given omega sequence. At most, one of them is true at a given omega sequence. And therefore, at most, one of them is an axiom in the best system of the omega sequence. The best system analysis of L star is much like that of, say, f equals g m1 divided by r squared. Think of constant g variations. Given any human mosaic, one needs criteria such as simplicity and informativeness, but we don't need the criterion of fit anymore to determine the best system. The usual problem associated with how to define fit will not arise for such humans. Okay, let me quickly come to some discussions and to a conclusion. An L star law may be thought of as either a generative Chen star law or probabilistic law constraining law. The notion of chance star or probability star are slightly different from traditional notion of chance or probability. How so? The results of coin tosses on L star satisfy every computable test for independence and will hence appear to be statistically independent. One might say the results are probabilistic star independent. But inasmuch as some sequences are impossible, physically impossible, there is also a sense in which the sequences, the full sequence, omega sequence, these results are interdependent. Also, we have a choice between Montan law of randomness and Schnorr randomness. This is computational kind of empirical determination. Still, the star laws already eliminate some forms of empirical determination. Unlike traditional probabilistic laws, by very much like deterministic laws, one will surely learn L star on complete evidence in every physically possible world. In contrast, if L is the true law, there will be a continuous cardinality of Maverick worlds such that if one were to inhabit any of them, one could never learn L from the results of any coin toss, for all the coin tosses. On the usual approach to think about laws, one needs some spectral background assumptions to overcome this difficulty. Assumptions like typicality, something like Cournot's principle, and principle. One needs to argue that whatever the law is, inhabiting a Maverick world of the true law is very, very, very unlikely or very atypical, such that one can neglect this possibility rationally. One needs to know that the world inhabits, and hence the physical nature of the sequence of records one has in fact recorded is typical or very likely given the true law. For any true law, there are Maverick worlds, but you should not think you live in the Maverick world of any true law. So you can infer what a true law is given by inferring based on the actual records and assumption that it is a typical sequence of the true law. Now, if an agent is simply presented with a sequence of coin toss records and knows nothing more than that she inhabits a physically possible world, then what happens? She cannot infer that the sequence exhibits the typical statistical properties given the true law. Such an inference requires her to appeal to a background assumption like the principle or Cournot's principle. And this assumption might be warranted, right, given other commitments one has. We can argue for this, we can support this with other arguments, but want to make this observation that they're simply not required in this case for empirical coherence if one focuses on star laws. You need them for L laws, but you don't need them for L star laws. That's a crucial difference here in terms of which assumptions we need. Okay, in conclusion, we've characterized two types of probabilistic laws using algorithmic randomness. A generative chance star law, and second, a probabilistic star constraining law. They provide a new way to think about probabilities and chances. We call them chance star and probability star. They address one variety of empirical underdetermination, but they also reveal other varieties that have been unappreciated so far. For all we know, our world might be characterized by a traditional probabilistic law like L or a star law. The notion of probability star constraining law has advantages over that of generative chance star law. It matches well with the holistic character of the constraints, directly supports a unified governing account of non-human laws, and provides independently motivated solutions to issues in the human best system account. Both notions are worthy of study and may lead to new ideas concerning the nature of laws. Okay, thank you for your attention.
Many thanks, Eddy, for this interesting talk.
Thank you, Ward.
So who wants to open the floor for questions? I see Barry. Barry, please go ahead.
Hi, Barry.
Hi, I'm not sure where's my microphone?
Yeah, we hear you.
Oh, I can hear you.
Wait.
We can hear you.
Can you hear me? Just 1 second. 1 second. Ay, ay, ay.
No worries.
1 second. Can you hear me at all?
Yes, I can hear you, Barry.
Oh, my microphone, by the way. Okay. Hey, Eddie, how are you? That was a great talk. You're thinking
Thank
about
you.
this very much the way I'm thinking about this stuff. Maybe that's not so surprising. I just have a quick first question, which is sort of just between me and you. Are you going to be in Portland?
Yes.
Great. Okay, we can talk about a lot of details about this. I'm really interested.
Wonderful.
That's where my microphone went. Okay, so here's something I didn't quite understand. I've been thinking about this from a purely Humean side, and I think to me that you gave a lot of good reasons to be a Humean in your talk. Maybe not. Maybe that's not what you wanted to do. But here's the question I have: if one was a Humean and once identified the laws in the Humean way, using the notion of fit in a way, and I do think that Elga's problems can be dealt with, but that's a side matter. I deal with them. But you then say that, look, we also can define your notion of L star law as the laws which don't suffer from we take all the undermining histories and we get rid of them, remove them. They're excluded.
Yes. Mm-hmm.
My question is that exactly the same set of nomically possible histories that your constraining laws pick out?
I think so. So the question is whether the non-Maverick worlds, the Maverick worlds are the undermining histories. And I think that,
right.
The usual examples of undermining histories fall in the Maverick worlds categories. Say the all heads worlds, or this sequence with 1/3 heads and 2/3 tails. We don't typically talk about the sequences with no relative frequencies, but I think they also fall under the undermining histories.
Well, let's see. So you don't literally have a proof that the nomologically possible worlds picked out by your constraining laws is exactly the same as the set of nomically possible worlds when the undermining worlds are excluded. You're just saying you think that they're going to be equivalent. Is that right?
So let's see. What will be a proof for this claim? It will be that what will be a precise characterization of undermining histories? It will be those histories such that the law is not the best system.
That's right. And of course, that would depend on what alternative best systems there might be. And so you need to make that more, more characterizable. So if you limit the number of alternative best systems, suppose you put alternative best systems have to be simple in very certain ways.
Right.
Okay.
Yeah.
Then you're going to get rid of more worlds, and I think that'd be more satisfactory, actually.
Oh, I see. So we're thinking of this doing a stepwise kind of process. You first restrict the laws using simplicity, for example. Think about all the L star laws with one law of randomness requirement, and then think about just changing the frequency constraint, say 1/2, 1/3, and so on. And this will give you destroying laws with destroying set of models.
Right. Okay. Well, the reason I'm saying this,
alternative laws will not have any intersection with the laws we're considering. It just be different carving in the space of possible sequences.
Let me see if I'm understanding. I don't want to take up too much time with this, but so let's see where we come to here. Is the set of nomologically possible worlds when you exclude the undermining worlds as nomologically impossible going to be the same as the nomologically possible worlds for your constraining laws? And the answer now is what?
I think yes, the same. set
Okay.
of worlds.
Then wouldn't you say that the Humean way of identifying these worlds is much more straightforward and simpler and much more connected with, scientific practice?
I don't think so.
Okay,
I think
that's one issue.
there's no straightforward argument for
And of course,
humanity.
the big issue is how in the world can constraining work? I mean, what is it that God looks at the whole history of the world and says, "Oh, we got to crush it into making." I mean, that's why I'm a Humean, but that's just a whole other
Right.
big issue.
Yes,
Okay,
that's right.
but we could talk about this when we see
Yeah.
each other. But thanks, it was a great talk and very, very helpful to me. So thanks
Thank
a
you,
lot,
Barry.
Eddy.
Thank you.
Thanks, Barry. So, Z?
Oh, by the way, Jeff, do you have anything to add on this question of undermining? And okay, I'll think more about this too, Barry. Thank you.
Thanks.
If not, maybe Z, Barry?
Okay, I think Gene might have been before me, but I'm already going.
I'm not sure. I just saw a bunch of hands suddenly, so I'm just.
I think Jean was one before. I think Zoom orders it in the sequence of
Okay.
Okay.
Hi, John.
Hi.
Hello.
It's my turn.
Hello.
Yes, it's my turn.
Oh, yes.
Oh, I'm sorry. Okay, thank you very much for the talk, which I thought was very illuminating. But I have a very naive question. What do you do if, as is the case always in physics, you have only access to a finite number of sequence of your random sequence? For example, you could have all ones, let's say, and this would be compatible being the beginning sequence of every of your random, whatever your criteria is,
Right.
Rothschild, whatever,
Yeah.
it would be compatible, but yet this would be considered evidence for a scientist that we are not playing with a fair coin, let's say, if it's a coin tossing, okay? So I think the way you do it usually in practice is by Bayesian updating.
Mm-hmm.
Assume that it's 1/2, 1/2, and then you get all ones, and then the probability that it's 1/2, 1/2 goes down the longer the sequence is.
Yeah.
That's the way I think at least, the way natural scientists work. Because you never ever have access to an infinite sequence, and every finite sequence compatible with anything you want on the infinite sequence.
Mm-hmm.
So that's my question.
It's a great question. So right now in this paper, we deal with a very simple setting with a very kind of godlike access in terms of the full world, right? It's kind of idealization that it would be great to think about the next step, which is connecting this to statistical tests and actual practice and how we infer the true laws. I mean, Jeff will have much to say about this, but just kind of one quick response is that, yes, this is an infinite case. And there are work on connecting this to Bayesian learning theory, such as work by Francesco Zeffiro-Blando and others, in showing that actually, I mean, one rough lesson is that the L-star law provides a very nice metaphysical background for thinking about how Bayesian updates can be successful or guaranteed to be successful. So there is the implicit connection to the epistemic side. People are still investigating how randomness might help with Bayesian learning theory.
I see.
And Jeff might have something more here too.
So yeah, this is just very quickly. This is a great question because real science is done on finite evidence. Our thought here, as Eddy suggested, was we wanted to give the best epistemic situation for the person who wants to discover laws. And the best epistemic situation would be one where you have all the evidence in hand. And in principle, you can survey it and you can do computations on it. And so that's what we wanted to grant. But the story needs to continue. There's more to it. Here's just a little bit more. A good Bayesian will be able to get evidence for a star law. And the way that works is that the Bayesian starts with the initial segment and always just has a finite amount of information at every time. And the good Bayesian tries to compress the initial segment. And this is a hard computational problem. But as the Bayesian has evidence that it can't be compressed beyond some C, and they go further and they can't compress it beyond that same C, and they go further and they can't compress it beyond that same C. The good Bayesian updater has increasingly good evidence for a star law. So getting evidence for a star law on finite segments is very much like getting evidence for a statistical law. And so standard Bayesian practice is supported by a view like this.
Yeah, but is there a big difference between having evidence for a random sequence, let's say, in the intuitive sense of the word, or evidence for a star law?
Yeah.
You see, of course, if you have 1, 0, 1, 0, 1, 0, then for finite sequence, but it repeats itself, then the Bayesian, of course, would say that's not random without having ever worrying about star laws.
Yeah, and the Bayesian will also say that's not represented by the star law. And so it's possible, depending on what the initial segment is, that the good Bayesian says, no, this doesn't look like a star law because I can keep compressing it more and more. But if the world is governed by a star law, then the good Bayesian is going to eventually come to that realization, not with probability 1, but guaranteed will come to that conclusion. And that's the difference here, is that the Bayesian in the limit has epistemic access to whether or not the full sequence of results is computationally equivalent in the computational equivalence class specified by B. Martin-Liff random. Now, even if I had full Turing computational power and I had the full omega sequence, as Eddy pointed out, there are some things that I can't determine. And among those things is I wouldn't be able to determine whether it was Martin-Liff random or Schnorr random. And even more troubling, I wouldn't be able to determine if it was Schnorr random, but not Martin-Liff random or Martin-Liff random. And so this is a new kind of empirical underdetermination. So the story is not pure goodness for the Bayesian in terms of what they have epistemic access to. It's better on a law like this than on a star law than it would be on a standard classical law.
Okay, thank you.
Thank you.
Okay, so I'm not sure who's next now, but is it Z or Joanna?
I think Z is next.
Okay, okay, I can't see it here. I don't know.
Hi, Z.
I'll help you out.
Hey, Eddy, thank you so much for this, Eddy and Jeff. This is really, really interesting. So I've got, I'm wondering about a couple things that are related but might not feel related. And so one of them is I'm sympathetic to some of what Jean was saying, and really, if you're just thinking about the epistemics of our relationship to laws, there's a lot of stochastic phenomena. Even things where they get their stochasticness from the fundamental, there's a lot of those things. We encounter them in a bunch of different ways. And when you're asking questions about the world being deeply misleading to us, we have to look at this sort of large and global thing. But one thing you might worry about is whether or not whether like really specific phenomena rather than, because it looks like this picture, and I might not have understood all of the technical moves, but it looks like this is a picture where there's sort of a feature of these sort of the global system of laws. And we can rule out things like maverick worlds that count as sequences for those things in their entirety, rather than say things that would count as mavericks for like one particular phenomena, like this one particular kind of decay, which is relatively rare or something. Or are you thinking that this sort of picture will end up being able to rule out maverick type worlds for each one of those processes, or is it some kind of like you take all all of the predictions of everything with the law together. And do you see what I'm asking?
Yeah, so we're looking at a very simple case of a repeated coin toss example. And what if like two kinds of coins, or a coin and quantum experiment and classical coin and quantum coin together, then things becomes tricky. Even for many particle system, right? How should we implement the constraints of randomness is a non-trivial question. So yeah, we have to look at a specific physical situation and see what is the right adaptation of the L-star law in that case. For a world like ours, say, for example, in Boolean mechanics, which is something we're trying to work on next, which thinking about how to implement L-star law for the probability distribution, say. That will be a goal to have. And then dynamical laws will take it over. But how to implement the kind of initial distribution using randomness constraint is a non-trivial question. But given that everything should follow from the position of the particles, then everything should, the apparent randomness, apparent stochasticity, apparent probabilities should be a consequence of derived theorems from the fundamental laws.
Right. Okay. So you are thinking these should be sort of bundled together in a way which I think this is the right, it would be, the reason I ask is it would definitely be a little bit weird if it turned out, if it just turned out that like our best way of understanding the laws involved multiple different like it's a system of like a bunch of different sort of independent laws that are all describing these different phenomena. They all have their own probabilistic thing. It'd be a little, you might worry that if these start getting too precise, it might be the idea of ruling out as impossible any maverick world, especially for, relatively minor parts of the phenomenon in the world, is an odd thing. But again, it's unclear how any of this is going to sort of exactly map onto a world more variegated than.
Oh, I see.
My
Yeah.
other, but my concern was, I was thinking that that accounts that involve, I like to call it pushy. I like nudging. Nudging was a very nice thing that you said. But any kind of the sort of pushy governing that gives either propensities or some other probabilistic oomph in the laws. I was a little confused by your criticism. I was initially thinking that, like, I mean, certainly if you're holding them to the same standards you are, they are going to be able to have like the chances of the sort of maverick world you're describing aren't just small, they're vanishingly small. Because if you're also only evaluating them in worlds where everything is infinite, and so you've got and so the chances of these things aren't just low, they're
exactly zero. Yeah.
Yeah. So like it's an odd, like it's you might worry that like that there's some of the strength of the argument against the sort of pushy pictures in favor of constraining might be a little weaker when understood that way. You might think also, right,
I don't think those arguments are decisive. I think that the pushy generative Chen star laws are, in Jeff's words, very sexy, with a kind of sexy kind of causal interdependence and cool nature of subtle violations of independence that we haven't thought about before. So it's great. We should all think about them. Now they're on the table. I was merely expressing some prejudices I might have, in the sense that if I were a pushy person, I would be very hostile to this kind of law. But maybe I was thinking about kind of a pushy kind of push conceptual law that's in a narrow box. If a general conception of production generation is not incompatible with it, it's incompatible with certain assumptions about causal locality. Yeah.
I mean, I do think that there is definitely a clear alignment of this sort of formal picture with, so I think of the constrainy type picture as basically one that takes the gnomic role of laws as its fundamental, as the like core basic thing that they do, and then tries to capture the other things that the laws do, more or less success and maybe some failure. But like you guarantee yourself gnomic and then see what else you can get. And so this picture, which turns probabilistic judgments into yes, no, is it nomologically possible or not, is definitely really well suited for that. I will say that like the things you lose if you're somebody who does care about governing, the kind of things you lose moving to that purely gnomic picture
I see.
Might be other things that would tell in favor of that. I do think that as a formal question, it's there are reasons for that, but I don't think it's as much about like that there are issues of how to deal with the low probabilities, and as much that like that
Right.
actually it's not even clear what a pushy conception of governing would be able to say about what the what possibilities even are. Like the they're gonna have to give if you wanted to be really, really strict about giving a pushy conception, I've got some on this, it would have to be something that is able to, from pushing, get you nomological notion.
Okay. Yeah, that's helpful.
That was all. I just wanted to throw that out. I was seeing the points there. I wasn't sure which one was the operative one. Okay, cool.
Okay, thank you, Zig.
Yeah, so 2 more hands, but I don't know who's next. Either it's Joanna or Nancy.
Joanna.
Sorry?
Joanna is next, I think.
Joanna, please.
At least Zoom thinks so.
Hi, Joanna.
Hi, thank you. I'd like to ask about some details of L star. So as you defined it, it's a conjunction of unbiased relative frequencies and randomness. And if I understood correctly, actually, just one of these conjuncts, namely unbiased relative frequencies, is able to do a lot of work you expect L star to do. For example, one of the problems you raised was that if we have just unstarred L laws, then we can laws with different probabilities are consistent with the same set of possible worlds, and this, if I understand correctly, this problem is already solved by replacing probabilities with those unbiased relative frequencies. So my question is, first, am I right? And second, if I'm right, what's the additional job to be done by that second conjunct, which is randomness?
Thank you. So the randomness constraint and the frequency constraint, sometimes I gloss them as separate, but they're the same. I mean, they combine together in the Monte law of randomness, given the background measure. So they should be thought of as the same constraint. And if we only have the frequency constraint, it's not going to be enough to rule out things like the alternating heads-tail sequence, or sequences with the right frequencies, but a simpler pattern. Simpler pattern we can explore for gambling, for, say, human for summarizing, or partially simpler law for other reasons. So in the cases of connecting the probability talk to actual practice in terms of gambling strategies, this will not going to be sufficient. And yeah, in the case of undermining histories, for example, the 101010 sequence is still undermining history, even though it's the right frequency. So it plays still this important role in all of these discussions. But you're right, the frequency would be enough to tear this apart into disjoint set of models. But randomness is a further constraint on which worlds exactly are the non-Mavic worlds. And for us, the randomness constraint is very crucial.
Yeah,
Okay.
I'll say something about this as well, because this brings up an important point about the toy example that we're using here of the quantum coin toss. If a sequence is Martin-Lerf random, then the relative frequency condition will automatically be satisfied. That is, it will be an unbiased sequence of coin tosses. So in that sense, when we give the condition Martin-Lerf random with unbiased relative frequencies, the little clause with unbiased relative frequencies is redundant. But we want to remind the reader that that's something that comes automatically with Martin-Lerf randomness. Now, if our toy example was not unbiased, relative frequencies, then we would need a little bit different notion than standard Martin-Lorf random. We would have to use a generalized notion of Martin-Lorf random that's appropriate to that unbiased case.
Thank you.
Thank you.
Okay, Nancy?
Hi,
Go ahead.
Nancy.
Hi. So I tend to be the pushy kind of person when if I'm going to do any metaphysics at all, because I don't like to start with a set and huge set of nomologically possible worlds and then worry about us being one of them. I'd like to think that, well, there's one world, we're in it, etc. And how then do we get this systematic behavior that's reflected in our laws? So I've had that idea that because it's the one world and it's just an artifact to think of. You get this set of nomologically possible worlds from starting with propensities in the real world. That's the idea. And then again, I've always assumed that if you've got a propensity, it's sort of supposed to have something to do with something that generates outcomes with a probability. I've always assumed that probabilities are, if you're going to have an infinite, a frequency interpretation of probabilities, that it's the limiting relative frequency in a random sequence. So let's start from that point and then think about the notion of governance. And again, trying to think about governance, I only have one way to do it, which is to use the metaphor of God, right? So God says, I like this law, right? This probabilistic law, and he tells St. Peter what to do. And he leaves it to St. Peter to carry out. But so this is going to be the probabilistic law, the random probabilistic Uriel star kind of law. And on one view, what St. Peter does is he creates this large set of nomologically possible worlds given that law, and he picks one of them, and that's the one that happens. But the other picture is St. Peter is very clever, and he creates a random outcome generator, and any random outcome generator has the appropriate propensity to produce a random sequence in the long run. And he sticks into the world all these random outcome generators that generate the outcomes one by one by one. But it's only one world, and it still employs the same technical notions, and it's still very metaphysically heavy in that in order to characterize the random outcome generator so far, what we have to do is characterize the sequences that it would generate. But at any rate, it's a way of getting your view, which fixed in with a kind of pushy view that takes propensities, but any propensity view has to already be generating random outcomes. It's having a propensity that has a probability in the other sense. It's just limiting yourself too much. So I'm only tacking on what I think is already there in the propensity view and claiming that it looks to me a nicer world where things happen one after another in history, and the constraint is by having to build this very odd machine that somehow knows how to generate a random sequence with a limit. Whereas if you didn't build in the randomness, it just had to generate a sequence where it knew that eventually it had that. Oh, I've had too many zeros. I better start generating ones. Anyway, so that's my sort of. I guess it's a question, or do you think I'm
Nancy,
right that? Do you think I can write that we can map the two views onto each other just like this, and then it's sort of so far a matter of is constraining from above or being able to build these masterful machines and things in the real world do. Our hypothesis when we make probabilistic laws is to hypothesize that coin flipping devices can be well modeled by as having propensities.
So Nancy, are you thinking that on a traditional propensity view, the maverick worlds can be generated or cannot be generated?
Well, on the traditional, I don't know. In the propensity view that I was brought up with, they cannot be.
Oh, they cannot be generated.
Well, yeah, I mean, you've got to, they will only generate Martin-Luff random sequences. So, I mean, I haven't looked at Shor because I did Martin-Luff a long time ago. So, but when I was teaching Popper's propensity view, I assumed that it would be generating random sequences. Now, I suppose that's because, already Kolmogorov and all that was. Anyway, sorry. So I take the traditional view to be not that it generates a probability sequence, right? With a
sure.
Yeah.
Well, that's really interesting.
But I take the traditional view not to be the one that starts with this set of omega possible worlds.
Sure. Yeah. I mean,
but it starts the way I always should have started post thinking about randomness from yonks before.
Yeah, that's very helpful. So that's interesting because I thought one of the hallmarks of propensity view is that it can still generate the maverick worlds.
I think it must depend on whether the person who's presenting it has thought about.
I see. Yeah, if you have read about Kolmogorov and Borel and all these guys, then you think that, well, this problem of probability to actual outcomes is really hard. So maybe it's natural to consider Martin-Luff random sequences that they are only possible outcomes. Okay, that's very helpful. Maybe Jack has something to say.
I can tell you that the group of people I was brought up with just took the limiting relative frequency interpretation of probability to be the limiting relative frequency and at random a Martin-Luff random sequence, or a Kolmogorov one if it was the generation before.
I see. So it seems like maybe this thread has been this is important. I should check it out in the literature too to see if propensity people have defended the Martin-Luff or L-star view.
Whether they just assume it. I mean, if I write about
maybe just assume that, yeah. I just want to say something about the pushing notion versus constraining notion.
Yes,
the two are not so different in terms of how I think about the metaphysics of laws. It's not like constraining laws have to be done by God from outside or devised on the outside the universe. But for me, the governing laws, the constraining laws themselves are primitive facts, fundamental facts that govern. I mean, there are facts that are just like other facts. It's just that they are more important facts, explanatory facts. So it's not like they are, they carry with them the space of possible worlds. The possible worlds are generated by the laws. So you can think of possible worlds as a way to gloss how the laws govern, not the ways in which laws govern. The actual world is actual, and that's what I fundamental postulate. And the actual world is a member of physical possibilities. That's how we understand constraining. But it's not like we'll have possible worlds, and therefore let's get something else to choose the actual world from.
No, I agree with that. It's just that I think I say the same thing in the propensity view.
I see.
Propensity, that's a primitive fact. It's the primitive fact.
Except there's one difference in terms of directionality. For propensities generation, there's a very fundamental conceptual metaphysical input about the direction of time. Start from 1 to 2 and 3 and 4, but not going backward. I will be confused if I go backward. I will be making conceptual metaphysical mistake. But for constraining people, for concerning conception, the conception of time's arrow is not fundamental, doesn't have to be fundamental. It can be bidirectional, constraint can be constrained in all directions. So the direction of time, I think here, is a crucial difference.
Yeah, no, right. And since I'm interested in causation and real causation in the real world, that that you pump up the laser, and that's how you get the beam out. So I'm looking at different issues than you, and I want to get causation back in.
I want to get causation back in too, but it's not fundamental causation.
Just differently, yeah.
Differently, yes.
Thank you. It's lovely.
Thank you, Nancy.
Yeah, thanks. Joanna, you had another question, sorry? Please go ahead.
Thank you. This is a follow-up question on that question about the possibility of checking whether a sequence is random based on finite initial segments, I think there is an important, a bit technical obstacle here, which is that, related to how this concept of Kolmogorov-Chaitin randomness works differently in the finite and infinite case. So in the this is often presented in the following way: we fix Turing machine, and whether a sequence is random or not depends on the length of the input that is given to this machine and produces the sequence. But then in an infinite case, one can show that this dependence on the choice of Turing machine disappears, but it is still there in the finite case. And one can show that for any finite sequence, there exists a Turing machine relative to which that finite sequence is non-random. So I wonder whether you have any thoughts on this difficulty.
Yeah, Jeff might have something to say about this, but very quickly, I was thinking that in the infinite case, you might have to replace the upper bound any constant c with some large number c. So you can think that it's not that infinite, it's not c incompressible, but with some large c, that it is not compressible.
Yeah, I can.
But in terms of
I can say this in a little bit different way. In the finite case, two different Turing machines, say one that runs by C++ and the other one runs by Fortran, and we're representing the codes. They might differ in the complexity that they assign the sequence, but the difference will always be within a constant. And for any two machines that we choose, and that constant will be the length of the code to compile one of the pieces of software in the other. And so the differences between the judgments for finite strings are to within a constant. And so that means that we're going to ultimately make the same judgments using two different Turing machines if we get far enough along the initial segment. And so this meshes with what Eddy was just saying. It might just be a larger C for one of the machines than the other, but there will be some C for which the initial segments can't be compressed any further, no matter which of the machines that we choose.
Thank you for your response. I'm aware of that result, but it doesn't reassure me because of what I said previously. There still will be some Turing machine such that relative to it, this particular finite sequence is non-random. And then we obtain a larger initial segment, and perhaps it will be random relative to that Turing machine, but there will be still another Turing machine relative to which it will be non-random, and so on.
So you can think of different Turing machines as fleshing out our computational abilities. So relativized to a particular Turing machine, you might have one notion of randomness, and which differ maybe by some constant with others. But yeah, so in the finite case, things get messy. It's not as precise and unique and definitive as in the infinite case. So this is one area in which the infinity really helps us. When we go to the finite cases, things become messy and maybe fuzzy and maybe vague. I'm happy with vague laws in general. Some think that probabilistic laws in the infinite case might not be vague, but in the finite case, we are kind of compelled to use fundamentally vague laws if the world is finite and if randomness constraint applies to finite sequences.
Thank you for your responses.
this might not reassure you, maybe make you more worried.
So I don't know if this will reassure you either, but of course what you're saying is right. It depends on which Turing machine I choose if I'm a good Bayesian. But I do take some comfort in the fact that if we have two good Bayesians, they choose different Turing machines on which to make their judgments on initial segments. If they consider enough evidence, the two Bayesians will converge to the same conclusion. And so right, they're not guaranteed for any specified finite segment, but that's all we had for the good Bayesians anyway. Is that that in the limit of inquiry, they will judge that their other Bayesian friends will end up in agreement. And so I don't think this is any worse than the standard epistemic sorts of problem that a good Bayesian inquirer faces.
But the L-star law does help the Bayesian a little bit more, in the sense that you get fewer under determination.
Just so, Eddy.
Right.
Thanks. So I see no further questions, but maybe I can ask one quickly. So, because Eddy, heard you saying we thought of applying that, for example, to Bohmian mechanics, this whole framework. So, and I was actually curious how that would go. Actually, can you briefly sketch that, or like in a many worlds theory? How do you actually rule out these maverick worlds?
Yeah, the concept of maverick worlds come from the quantum mechanical discussion about maverick branches, maverick worlds in many worlds.
Or maybe if I can add something else. So, like these statistical regularities, for example, they come up if you do experiments. Okay, but suppose no experiments were going on in the world. I can imagine that you can still say something, but maybe you can just immediately say how you see it.
Yeah, so Jeff, you might feel free to jump in. So we are still working on this part of the project, extending this to more realistic physical theories. But for the Bohmian randomness, it comes from initial conditions. So it would be natural to consider how to generalize an L-star law for, say, a distribution of particles, actual distribution of particles at T0.
So there's one actual configuration.
Not one actual. I mean, there's one actual one, but we're going to consider a subclass of all possible ones as the nomologically allowed initial conditions.
Okay. And what's the condition? So which ones are going to be allowed? Can you? Is there a precise way to formulate that?
So this is something Jeff and I are still working on. Jeff, would you like to say a few words about this?
Because, for example, also the initial state of the universe is probably not going to be a product state. Okay.
Yeah.
Right. We have entanglement. Yeah. Mm-hmm.
Yeah. So here's one approach, and I don't know what the best way to do this is, but the problem is, as Eddy described it, we need to have some way to specify that initial state, and the thought might be something like this. Suppose we're in Bohmian mechanics and we consider the wave function in configuration space, in 3n-dimensional configuration space. Choose a partition in the space. And the way we're going to do this is we take the wave function and choose some one of our 3n coordinates. With respect to that coordinate, let's chop the wave function in half so that half of the norm squared of the amplitude is on one side of our partition and half of the norm squared of the amplitude is on the other side of the partition. Then take the first bit of a Martin-Löf random sequence, and it tells us which side of that partition our initial configuration is. So if the first bit is 0, we're on the left-hand side on that partition. If the first bit is 1, we're on the right-hand side on that partition. Now choose another one of your 3n coordinates and partition the wave function into half norm squared amplitude on one side of that partition and half on the other side. use the second bit to determine which quadrant you're in now, the second bit of your Martin-Lorentz sequence. And so by this mechanism, a Martin-Lorentz sequence, the full Martin-Lorentz sequence, will precisely determine the initial configuration of the system. And the initial configuration of the system will satisfy the standard expectations with respect to being randomly distributed with respect to the wave function according to the norm squared. So if I assign my expectations, if I know that this procedure was used, then at time t0, I'm going to assign the standard expectations, the quantum mechanical expectations for the initial configuration relative to the wave function. Now, this is going to handle all the entanglement issues because we're doing this in the context of configuration space. So the wave function already represents all the entangled degrees of freedom between the particles. This is one way that we might do it. I'm not sure.
Can I interrupt you? So, and would that also guarantee that if in that universe a sequence of experiments was done, so the universe evolves, is interacting, and then you do measurements at certain times, Stern-Gerlach measurements, would that guarantee that, for example, the results of these measurements would also be Martin-Löw?
Good. That's exactly the next question that one should have. And the answer to that is no, it's not going to guarantee that. But if you choose your axes in an arbitrary way for performing these Stern-Gerlach experiments, you should expect that the standard quantum probabilities will obtain. And so you have an L-star law for the initial boundary condition, but that on this proposal that I'm suggesting now does not guarantee L-star results as you perform the experiment. And so that's one of the trade-offs of the proposal that I was just describing. But this is stuff that Eddy and I are still thinking about. But since you asked such good questions, Ward, I thought you might be interested in some of the details. And clearly, you've glommed on to what the issues are here.
Okay, thanks a lot.
A pleasure.
Anybody else? If not, so let me thank Eddy. Z, yeah, just in time, Z, please.
Sure. Hold on. Do I even exist anymore? I do. Okay, cool. So, I mean, I'm tempted actually to ask a question about the difference between guaranteeing L results and when you should expect things to match the predictions of QM, but I was puzzled by an answer that Eddy gave when he was talking about, but the pushy and constraining conceptions are very similar except for issues of directionality in time, where I think that it's probably right that there are some strong restrictions on what would count as pushy governing or propensities or whatever you want to call those. It's not as obvious to me that that things are completely rosy on the constraining side. So my issue is basically this. It's certainly true that you might be able to define up something that you can call that, but it's not going to, your sort of pitch is like, we've got this one basic conception, constraining. What does constraining do? Constraining is this thing that lets you, that the laws carry with them a determination of which possible worlds are nomologically possible, which are not. So it's got gnomic, the gnomic rule of laws is built in and everything flows from that. Certainly you might then be able to say, well, given the structure of what the laws say and given what's in the world, we can say that the combination of like what the laws say and what's in the world will mean that the future will be this way, or what the laws say and what's in the world will mean that the past will be this way. And you could define up some like conditional looking thing and call that constraining for your, is that the sort of thing that you were thinking as being like in the vicinity of that move?
In terms of recovering causal talk and
either
so on.
Directionality or some bidirectionality or
right.
Yeah.
You might use conditionals, you might use further boundary condition laws and so on to like the past hypothesis law to get
Sure,
those
sure.
conditional from the laws. Yes, but I think that maybe it's not just direction of time per se, but also here's kind of extreme example. Closed time-like curves is straightforwardly incompatible with, say, modeling's version of the productive view, and they think that self-production is conceptually impossible. So for full general relativity is not right. We have to restrict it somehow. But there's no fundamental problem with regarding the full Einstein equation as the fundamental law on a constraining picture. So just kind of more generally, there are cases in physics we think that, so Sheldon Gosling and I think that the constraining view is more suitable as a starting point for discussing the metaphysics of laws. That for us, our notion of laws are much wider than, say, modeling's version.
Sure. The reason I was saying that feels like there's an issue there, which is that the kind of thing that the laws are doing that are able to recapture some amount of directionality, whatever that is, you can define, like, it's not going to be that they do it by a directional, like, constraining. The governing that they do is just that thing that operates only at the level of coarse-grained of whole worlds and determining if they're nomologically possible or necessary, and then it's the or nomologically possible or not, and then you might be able to then say some conditional thing about what's going on within the worlds, but it's not going to be the case that the constraining is operating within the worlds in a sense that it is the same kind of constraining as the one you were talking about before. It's like there might be a consequence of it somewhere down the line.
Right, maybe
the same is going to be true to save like a Maudlin style view for like a closed time-like curve. You might be able to get the floats to generate it in some sort of unique way, but it is certainly true for each stage that there is I don't know. It's not obvious to me that these are going to be that different.
Well, in that case,
recognizing
I think
how much it's not coming from your core conception, directionality, the ability to recapture this sort of really flexible notion of directionality, right?
I do think the directionality comes from the core, and this is one of the point that Chen and I make in our paper, focusing on the governing as constraint and governing as production. And one of the key idea is the directionality. And you see this in the powers view twice over because of how you think about propensities, capacities, and also how explanations work, say, had a Demarest account. And you think see this again in even Platonic versions of universals, and especially in Maudlin's view, it's very explicit. And it seems like it is the core of the production idea, generative laws, that it has this built-in fundamental error. The only exception you see is, I think, Barbara Vedder's book has one footnote, bidirectional powers or potencies. So yeah, and I don't even think that she focus on it because she thinks that's kind of a non-standard view. So focusing on the ones with a clear directionality. But we can talk more about this at some point. I do think that a constraining view, the one advantage is that you don't need the direction to make sense of how laws govern. And for this reason,
I definitely agree with that part. I was wondering whether or not you could get it, or you could get something like, because there's a difference between like, oh, we're not bound to this, and oh, we actually can't recapture this if you thought it was important, right? That
Right. I do think we can recapture this if you think it is important. And that's why temporally asymmetric boundary conditions, even this law, the L-star law, is directional in the presentation here. You start with the first toss and the second toss and the third toss. There's a way to think of this in a symmetric way, but naturally can think this as a somewhat asymmetric law, right? In the past hypothesis, it's also asymmetric in time. So given the temporal asymmetries, you'll be easy to get back the temporal asymmetries in the explanations. But if you have purely time-symmetric laws, it is it's going to be a different picture.
We can talk about it. Oh, good.
Okay.
This is something connected to what Ward was asking earlier, and so I wanted to say something about what we know and what we don't. In the Bohmian case, the procedure that I described, here's what we know. We know that if you carry out this procedure at the initial time, then there will be a way to choose your spin measurements in such a way that you're not going to be guaranteed to get a Martin-Liff random sequence of results relative to the axes that you choose your measurements on. What remains an open question is if you choose a single axis on which to make all of your measurements from then on, whether you're guaranteed. It may be that you are guaranteed in that case that you get a Martin-Liff random sequence. And that remains an open question. That it's tricky. Eddy and I have played around with trying to get a proof for this, and it still escapes. I can't get my head around it. So if anyone has good ideas about how to address the open question, that's great. We should talk. But that's where we are in the process. And so I wanted to pin this down. The thing we know is that it's not going to guarantee, right? I could reverse engineer. I can look at the generator Martin-Liff sequence and choose measurements that are not going to be quantum mechanically distributed, Martin-Liff guaranteed distributed. But if I choose a single axis, I don't know. That remains an open question. So I just wanted to say that so that everybody's clear about what the frontiers look like here.
Okay, thanks, Jeff, and thanks, Eddy and Jeff, for this wonderful talk and the great discussion. I don't know if Dirk wants to announce the next speaker.
May always have the last word.
Yeah.
Okay, thank you again to Eddy and Jeff for the presentation. So I just want to leave you with that. At the 21st of this month, Michael Drusen will give us a heads up on the search for bosons beyond the standard model with atomic ions. So it would be nice if a couple of you will join us. It's not on the website yet, but will be there soon. And yeah, I wish you a good time in between and hope to see a lot of you soon. Yeah, so since I have the last word, I say goodbye, guys. Stay safe.
Thank you. Thank you, Dirk. Thank you, Ward. Thank you, everyone.
Thank you so
Jeff.
much.
Eddy,
Bye.
well done.
All right.
Have a nice
thank you.
day.
Mhm.